Ever wonder why every single race car on Earth, from a $50 million Formula One machine to a weekend warrior dirt tracker, uses plastic windows instead of glass? Most people assume it's just about safety. Some think it's a weight thing. But the real story goes so much deeper than that, and it traces back to one stubborn, brilliant, rule-bending mechanic who lived at a NASCAR stock car in 1968 and saw 75 pounds of wasted potential hiding in plain sight. What he did next didn't just change one race team. It rewrote the engineering playbook of every form of motorsport on the planet, influenced the design of production supercars, spawned entire new industries, and proved that the most revolutionary ideas often come from questioning something everybody else accepts as obvious. The name is Smokey Yunick. And if you haven't heard it yet, buckle up, because this story is about to completely change how you think about innovation, racing, and the sacred cows we never think to question. This is Legacy Motoring, and I spend way too much time thinking about the engineering decisions that quietly shaped motorsport forever. If you're someone who loves digging into the real history behind racing technology and understanding why race cars are built the way they are, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, here's the thing. Before we get into Smokey Yunick and what he actually did, we need to understand the world he was operating in, because context matters enormously here. The late 1960s NASCAR paddock was a completely different universe from what we see today. There were no wind tunnels. There were no computational fluid dynamics simulations. There were no teams of aerodynamicists with engineering degrees from MIT running finite element analysis on door handles. Instead, there were guys like Smokey, brilliant, intuitive, relentlessly curious mechanics who learned everything they knew by doing it wrong first and then figuring out why. Teams operated out of converted gas stations, backyard garages, and buildings that were one strong wind away from becoming kindling. The rulebook was thin enough to fold into your back pocket, and the cars themselves, they were brutally magnificently simple. Think about what a late 1960s NASCAR stock car actually was. You're looking at a big block V8 engine producing somewhere in the neighborhood of 500 horsepower, a 4-speed manual transmission, a solid rear axle, drum brakes that would fade into uselessness after 10 hard laps on a superspeedway, no power steering, which meant drivers needed forearms like structural steel just to wrestle these things through the corners at Daytona. We're talking about 3,400-pound missiles that were held to the road by technology that honestly belonged in the 1950s. And the glass, oh, the glass. A typical NASCAR windshield in 1968 weighed between 25 and 30 pounds. The rear window added another 20 to 25 pounds. Side windows, if a team hadn't already removed them for airflow reasons, contributed another 10 pounds each. Those little triangular vent windows, remember those? Added another 5 pounds per side. Add it all up, and the glass package on a stock car easily exceeded 75 pounds total. That's the equivalent of bolting an extra human being to the roof and asking your engine to drag them around a super speedway for 500 miles. And here's what most people don't realize. Nobody was questioning it. Not a single team in the entire paddock was sitting there thinking, hey, wait a minute, does this stuff actually have to be glass? It was just accepted. It was always done that way. The rulebook required windows. Windows were glass. End of conversation. Until Smokey Yunick started having a very different conversation. Now, you might be thinking, come on, how big a deal can window weight really be in a sport where horsepower is everything? And look, I get that instinct completely. But here's where it gets really interesting. And this is where most racing fans fundamentally misunderstand performance physics. In racing, engineers have a saying that has been repeated in every garage from Daytona to Monaco. Adding power makes you faster on the straights. Removing weight makes you faster everywhere. Let that sink in for a second. Everywhere. Not just in a straight line where you can feel the difference in acceleration, everywhere. Every corner entry, every mid-corner balance point, every corner exit, every braking zone, every transition between them. Weight is the enemy that never sleeps, and 75 pounds is not a trivial number when you're trying to find tenths of seconds in a sport where victories are decided in thousandths. Consider the physics in terms that actually make sense. A car's ability to brake is limited by the friction between its tires and the track surface. More weight means more force required to decelerate. More force required means longer braking distances. Remove 75 pounds, and you can start braking later. Carry more speed into the corner, and carry that speed advantage through the entire corner exit and down the following straight. The effect compounds itself every single lap. Cornering physics work the same way. The centripetal force required to keep a car on a circular path through a corner equals mass multiplied by velocity squared divided by the radius of the corner. Less mass, same speed, same radius, less force required from the tires. The tires don't have to work as hard to maintain grip. They run cooler, they wear more slowly, you can run them softer, which means more grip throughout the stint, which means faster lap times from start to finish, not just on fresh rubber. And acceleration, the part everyone thinks about first, follows Newton's second law directly. Force equals mass times acceleration. Same force from the engine, less mass to accelerate, more acceleration. In a 500-mile race with dozens of restarts and acceleration zones out of every corner, those gains accumulate into something undeniable. According to research on weight reduction in motorsport, every 100-pound reduction in vehicle weight translates to approximately a 0.3 to 0.37 second improvement per lap on a typical superspeedway. Scale that across the full 200 laps of the Daytona 500, and you're talking about a minute of time advantage from weight alone. A full minute from windows. Smokey Yunick understood all of this intuitively, which is what made him dangerous to the competition and occasionally to the NASCAR rulebook. He wasn't just a mechanic. He held dozens of actual patents. He was an inventor, a self-taught engineer, and arguably the most creative problem solver the sport has ever produced. His shop in Daytona Beach, Florida, called the best damn garage in town, and yes, that was the actual sign on the building, was less a race shop and more a laboratory where the boundaries of possibility were constantly being probed, poked, and occasionally detonated. This was the man who built a 7/8 scale Chevrolet that looked completely normal to inspection officials, but was smaller in every dimension, making it significantly more aerodynamic. He routed fuel lines through the entire length of the car to effectively carry 5 extra gallons past post-race fuel checks. He once inflated a basketball inside a fuel tank after technical inspection to displace volume and create hidden capacity. Smokey's approach to racing was built on one foundational principle. The rulebook tells you what you cannot do. It says nothing about what you can do. And if it doesn't specifically prohibit something, it is absolutely fair game until they write a rule to stop you. Glass windows. The rulebook required windows. It required them to be transparent. It required certain minimum dimensions. It said absolutely nothing about what material those windows had to be made from. That gap in the regulations was about to become the most consequential loophole in NASCAR history. The material Yunick had his eye on was called Lexan, a polycarbonate resin developed by General Electric scientists in 1953. And the origin story of this material genuinely reads like something from a Cold War spy thriller. Lexan was initially developed for classified military applications: fighter jet canopies, astronaut helmet visors, blast shields, ballistic barriers. The stuff was extraordinary. It was 250 times stronger than conventional glass when subjected to impact forces. It weighed roughly half as much per equivalent volume. It could be heated and formed into complex curved shapes without losing its structural integrity. It was optically clear, resistant to ultraviolet degradation, and could absorb the kind of impacts that would turn a glass panel into 1,000 flying razor blades. The aerospace industry had been exploiting these properties for years by the time Yunick got interested. The windows on Apollo spacecraft were made from polycarbonate. Military helicopter bubble canopies relied on it. The material existed. It was proven. It was available if you knew the right people and were willing to spend serious money. Nobody in NASCAR was thinking about it because nobody in NASCAR was looking at aerospace material catalogs. Nobody except Smokey Yunick. Sourcing the Lexan itself was the first challenge, and it was a real one. In 1968, you could not simply call a supplier and order sheets of aircraft-grade polycarbonate. This was specialized material with almost exclusively military and aerospace applications. Yunick had to leverage a network of contacts built over decades of consulting work with various aerospace and defense contractors, calling in favors, working angles, and convincing people to sell him a material that had never been used in motorsport before. The cost was eye-watering by the standards of the era. Lexan ran nearly 10 times the cost of equivalent glass by square footage. For a garage operating on a racing budget in 1968, that was a significant investment based entirely on a theory that had never been tested in competition. But Smokey Yunick had run the numbers in his head and liked what he saw. Installation was its own engineering challenge, and this is where Yunick's crew spent weeks learning lessons that no manual could teach them because no manual existed for this application. Lexan behaved nothing like glass during installation. It expanded and contracted at dramatically different rates than the steel body surrounding it when temperatures changed, which in a race car environment meant it changed constantly and significantly. Mount the windows too tightly and thermal expansion would cause the Lexan to buckle and distort in the heat of a long race. Mount them too loosely and the vibration frequencies of a racing engine would rattle them to structural failure within a handful of laps. The solution required custom-designed rubber gaskets and mounting hardware with oversized holes that allowed thermal movement without compromising security. Yunick's crew also discovered that Lexan scratched with startling ease compared to glass. A belt buckle dragged carelessly across the surface during installation could leave permanent marks. Standard glass cleaning products caused permanent hazing. Paper towels created micro-scratches that accumulated into significant visibility problems over time. They learned to apply protective films during installation and removal, to use only specific cleaning compounds, and to handle the material with a care that felt almost excessive in a garage environment where engine blocks got dropped with casual regularity. But when they put the car on the scales, every single hour of that painstaking installation process was immediately justified. The weight savings exceeded even Yunick's optimistic projections. Not only was the Lexan itself dramatically lighter than the glass it replaced, but the mounting hardware could be substantially simplified. Glass required heavy-duty frames, thick rubber seals, and robust retention systems designed to prevent catastrophic shattering in a crash. Lexan, being fundamentally flexible and impact-resistant by nature, could be secured with lightweight aluminum frames and simple fasteners that added almost nothing to the total weight equation. The final tally approached 75 pounds of savings from a single modification. 75 pounds. In the sport where crew chiefs celebrated saving 3 ounces by drilling holes in brake pedals, Yunick had just found the equivalent of a buried treasure chest sitting in plain sight on every car in the paddock. The performance gains showed up immediately, and they showed up everywhere, exactly as the physics predicted they would. Acceleration from pit road speed to racing speed improved measurably. Braking distances shortened by several feet from race speeds, which on a superspeedway translates directly into later braking points and higher corner entry speeds. The car responded to steering inputs with noticeably less inertia, meaning it changed direction more eagerly and more precisely, which allowed drivers to be more aggressive with their corner entries without unsettling the balance. Tire wear improved because there was simply less mass being forced through every corner, reducing the lateral loads that scrub rubber from the contact patch. Even fuel consumption dropped slightly because the engine was working against less resistance to maintain racing speed. Every single metric that matters in racing improved simultaneously from one modification. That almost never happens. Usually you trade one benefit for a cost somewhere else. Aerodynamic downforce costs drag, mechanical grip costs tire life. Stiffer suspension improves cornering but hurts traction on bumpy tracks. But weight reduction at this scale delivered nothing but gains across the entire performance envelope, which is why engineers spend so much time and money chasing it. Here's what most people don't realize about the specific weight distribution advantage that came with removing the glass. The windows on a stock car sit high on the vehicle. The windshield, the rear glass, the side glass, all of it is positioned well above the car's center of gravity. When you remove weight from high positions on a vehicle, you don't just reduce total mass. You lower the center of gravity, and that has implications for handling that go beyond simple weight reduction math. A lower center of gravity reduces weight transfer during cornering, which means the outside tires don't get overloaded as severely and the inside tires maintain more contact with the track surface. The entire car becomes more balanced, more predictable, and more responsive to setup adjustments. Smokey Yunick hadn't just removed weight, he had removed weight from the worst possible place it could have been, sitting high up on the car, fighting the driver's ability to maintain control through every single corner. Now here's the thing about how the competition reacted when Yunick's Lexan windowed car rolled out onto the track. The initial response was confusion rather than outrage, which is actually telling. Other crew chiefs noticed something was different. They could see it. They could hear the different sound when the body flexed. They could see the subtle optical qualities that distinguished polycarbonate from glass when the light hit it at certain angles. But they couldn't quite articulate what they were looking at because nobody had ever considered looking for it. It was genuinely outside their frame of reference. When teams finally understood what Yunick had done, the garage split almost perfectly down the middle. Half the crew chiefs were furious, claiming Yunick had gone too far this time even by his own legendary standards of creative interpretation. The other half said nothing publicly and sent someone quietly to find out where you buy Lexan in bulk quantities. NASCAR officials found themselves in an awkward position that sanctioning bodies have faced repeatedly throughout motorsport history. A competitor had done something that violated the spirit of the regulations without technically violating the letter of them. The rulebook required windows. It required transparency. It required certain safety standards. Yunick's Lexan met every single written requirement, and in some crash scenarios it actually exceeded the safety performance of conventional glass by remaining intact rather than shattering into projectiles. This is where it gets really interesting from a regulatory perspective. NASCAR's options were essentially threefold. They could ban Lexan windows by writing a new rule specifically prohibiting them, which would make the sanctioning body look reactive and arbitrary. They could approve them with specifications, essentially legitimizing Yunick's innovation and allowing everyone to use it. Or they could do nothing, which would allow the performance advantage to persist for whoever was willing to adopt the technology. They chose option 2, and they chose it relatively quickly by the standards of regulatory bodies in any industry. Within 2 seasons, Lexan windows were explicitly approved in the NASCAR rulebook with specifications governing minimum thickness for different window positions, approved grades of polycarbonate, and required installation methods to ensure consistent safety performance across the field. The sanctioning body recognized something important. This wasn't just a loophole being exploited. It was a genuine technological improvement that made the cars faster and safer simultaneously. Banning it would have been difficult to justify on any rational basis. The adoption curve that followed was steep and nearly universal. Teams that had the resources moved to Lexan windows almost immediately once official approval came through. Teams that were slower to adapt found themselves at a measurable competitive disadvantage that they couldn't compensate for through other means. Within a few seasons, finding a serious NASCAR competitor still using conventional glass windows would have been like finding one still using bias-ply tires after radials were proven. The technology didn't just win arguments. It made the arguments irrelevant by simply performing better in every measurable way. And performance wins every argument in racing eventually, no matter how much tradition or sentiment or competitive self-interest tries to stand in the way. The ripple effect spread outward from NASCAR faster than anyone anticipated. IndyCar teams, who operated in a culture that was arguably even more obsessed with weight reduction than stock car racing, saw the Lexan data and made the switch with minimal resistance. Formula One, which had a reputation at the time for being somewhat insular and resistant to adopting innovations that hadn't originated within its own ecosystem, began experimenting with polycarbonate windows within just a few years. Drag racing adopted the technology almost overnight, which made complete sense given that drag racing is in many ways the purest expression of the weight reduction philosophy. Every pound you remove from a drag car translates with almost perfect linearity into improved elapsed times and higher terminal speeds. The quarter-mile stopwatch is brutally honest in a way that road course lap times sometimes aren't, because there are fewer variables to hide behind. When the drag racing community saw what Lexan windows did for weight, the conversion was essentially instantaneous. Look, the spread wasn't just contained to professional motorsport either, and this is the part of the story that most people completely miss when they talk about Yunick's Lexan innovation. The technology migrated upward into production performance vehicles with a speed and completeness that genuinely surprised even the people involved in making it happen. Ferrari, not a company known for following trends set by American stock car mechanics, used Lexan windows extensively in the F40, which was introduced in 1987 and is still considered one of the most significant supercars ever built. The rear window and side windows in the F40 were polycarbonate, contributing to a total vehicle weight that allowed a modest 478 horsepower engine to produce genuinely supercar performance. Porsche offered polycarbonate rear windows as part of lightweight packages for their Track Focus 900 and Lemon variants throughout the 1970s and 1980s. Lotus, whose entire design philosophy could be summarized as adding lightness, embraced polycarbonate glazing across multiple models. What had started as a workaround to a regulatory gap in a regional American racing series had become a standard tool in the global high-performance automotive engineering toolkit. The economic implications deserve serious examination because they extended well beyond the racing industry itself. General Electric's Lexan product line saw demand from motorsport applications help drive investment in manufacturing capacity and material refinement that benefited every other application simultaneously. Companies that had never considered the racing market as a revenue source suddenly found themselves with relationships with NASCAR teams, Formula One constructors, and sports car manufacturers. Material scientists who had spent their careers on military and aerospace contracts were being hired as consultants by racing organizations that wanted to push polycarbonate performance further. New grades of material were developed that offered improved optical clarity, better ultraviolet stability, enhanced impact resistance at elevated temperatures, and surface hardness treatments that addressed the scratching vulnerability that Yunick's crew had struggled with during those early installations. The racing industry didn't just consume the technology, it actively participated in advancing it, creating a feedback loop between motorsport and material science that produced innovations benefiting every downstream application. Consider also the safety implications because this is genuinely important and often gets overshadowed by the performance story. According to data compiled by NASCAR's own safety research program, the transition from conventional glass to polycarbonate windows eliminated an entire category of injury that had been a consistent presence in crash reports throughout the sport's earlier history. Flying glass fragments from shattered windows had caused lacerations, eye injuries, and in several documented cases, injuries to marshals and trackside officials positioned near crash sites. Polycarbonate simply does not shatter into sharp fragments under impact forces. It deforms, it cracks, it may ultimately fail under sufficient force, but it does so in ways that are dramatically less likely to create high-velocity projectiles. The same property that made it attractive for bulletproof barriers and fighter jet canopies made it genuinely safer in racing crash scenarios. Yunick had gone looking for free speed and accidentally found a significant safety improvement at the same time. That combination, better performance and better safety simultaneously, is extraordinarily rare in engineering and helps explain why the adoption was so rapid and so complete. Now, you might be thinking at this point that all of this sounds almost too clean, too perfectly positive, as if the Lexan windows had no downsides whatsoever. And look, that would be a fair skepticism, because in engineering, there is always a trade-off somewhere. Lexan did have real disadvantages that teams had to manage carefully. The scratching vulnerability we mentioned during installation didn't disappear once the car was on track. Racing environments are full of debris. Sand, rubber marbles thrown off the racing surface, small stones, particles of tire and track surface, all of it gets thrown at the windows at high velocity during a race. On glass, this produces minor surface wear over time. On Lexan, particularly early generation Lexan without surface hardening treatments, it produced accelerated optical degradation that could compromise driver visibility within a single race distance. Teams had to develop tear-off film systems, multiple layers of thin, transparent film bonded to the window surface that a crew member could peel away during a pit stop to reveal a fresh, clear surface underneath. The tear-off system became standard practice across motorsport, and today it's so universal that fans watching pit stops can see crew members grabbing the corner of the windshield film and stripping it away in a single practice motion. Heat management was another genuine challenge. Polycarbonate has a lower continuous surface temperature than glass, and race car interiors routinely reach temperatures that would surprise most people. Measurements taken inside NASCAR cockpits during summer races at tracks like Talladega and Phoenix have recorded ambient temperatures exceeding 140 degrees Fahrenheit, with localized hotspots near exhaust routing and transmission tunnels reaching significantly higher. At sustained elevated temperatures, early-grade Lexan would begin to soften slightly and deform under the aerodynamic loads pressing against it at racing speeds. Windows that had been flat and optically perfect in the garage would develop subtle bowing that created visual distortion at speed. Teams learned to add additional support structures behind the window panels in areas most susceptible to aerodynamic loading, and material suppliers responded by developing higher temperature grades specifically for motorsport applications where cockpit heat was unavoidable. The ultraviolet degradation issue was another problem that only revealed itself over time and with real-world exposure. Early Lexan formulations, even those considered UV stabilized by aerospace standards, would develop a progressive yellowing when subjected to prolonged sun exposure combined with the thermal cycling of repeated race use. A windshield that was optically perfect at the start of a season might have a distinctly amber tint by the final races, subtly distorting color perception and reducing light transmission in ways that affected driver visibility during the critical transition periods between bright sunlight and the shadows cast by grandstands and pit lane structures. Drivers began reporting that they could sense the degradation even when they couldn't consciously quantify it, a vague sense that something was slightly off with their perception of the track surface ahead. Material scientists responded by developing increasingly sophisticated UV stabilizer packages that were compounded directly into the polycarbonate resin during manufacture rather than applied as surface coatings, which proved far more durable under the combined assault of heat, sunlight, and chemical exposure that defined the race car environment. The chemical compatibility issue was perhaps the most immediately dangerous of the early challenges. Polycarbonate, despite its extraordinary mechanical properties, has a notable vulnerability to certain classes of organic solvents and fuels. Gasoline, in particular, certain aromatic hydrocarbon components present in high-octane racing fuel formulations could cause surface crazing and internal stress cracking in Lexan panels that had been exposed to spills or even vapor concentrations over extended periods. A window that looked perfectly intact visually might have developed microscopic internal crack networks from fuel exposure that would cause it to fail catastrophically under impact forces that an uncompromised panel would have handled without difficulty. Teams discovered this the hard way during refueling operations when fuel overflow made contact with window panels, and the subsequent damage wasn't apparent until a later inspection revealed the internal cracking. The solution required both improved material formulations with better solvent resistance and stricter handling protocols that kept fuel away from window surfaces during pit operations. It also drove the development of protective coatings that could be applied to the exterior surface to act as a chemical barrier without compromising optical clarity. Here's what most people don't realize about these early challenges. Rather than undermining the case for Lexan windows, working through these problems actually accelerated the development of polycarbonate technology across every application where the material was used. The motorsport industry, because it operates at performance extremes that reveal material weaknesses rapidly and completely, became an extraordinarily effective testing ground for improvements that then benefited every other application. The UV stabilizers developed to prevent racing windshield yellowing improved the longevity of polycarbonate in architectural glazing applications. The surface-hardened treatments created to protect race car windows from debris scratching became standard in eyeglass lens manufacturing. The high-temperature grades developed for racing cockpit applications found use in industrial equipment operating in high-heat environments. The chemical-resistant formulations drove improvements in polycarbonate used in chemical processing equipment and laboratory applications. Motorsport had inadvertently become a development partner for the entire polycarbonate industry, stress testing the material in conditions no laboratory could fully replicate and driving improvements that benefited millions of end users who had never watched a race in their lives. This pattern of motorsport driving broader technological development is one of the consistent themes running through racing history. But the Lexan case is particularly interesting because the flow of influence ran in both directions simultaneously. Racing took an aerospace material and stress tested it in new conditions. The insights generated fed back into the material science community and drove improvements that then came back to racing in better product generations. It was a genuine collaborative development loop that neither party had explicitly planned or organized. It happened organically because the performance demands of motorsport were uniquely capable of revealing both the potential and the limitations of the material in ways that mattered for practical applications across multiple industries. Now let's talk about Smokey Yunick the man in more depth, because understanding his personality and his broader body of work is essential to understanding why the Lexan windows weren't a lucky accident. They were an inevitable product of a specific kind of mind operating in a specific way. Yunick stood 6 feet tall and moved through the world with the absolute confidence of someone who had taught himself everything he knew and had been proven right often enough to stop doubting his own judgment. The cowboy hat was permanent. The cigarette was permanent. The willingness to tell NASCAR officials, team owners, sponsors, and anyone else exactly what he thought of their intelligence was also permanent, which explains both why he was banned from the sport multiple times and why he kept coming back. Because the people who banned him needed him more than he needed them. His formal education ended early. He had learned engineering by doing engineering, by taking things apart and putting them back together differently and seeing what happened, by asking why about things that everyone else simply accepted, and by refusing to be satisfied with answers that amounted to because that's how it's done. He held dozens of patents across a remarkable range of technical fields. Not all of them were racing related. He worked on engine efficiency problems, on fuel delivery systems, on material joining techniques, on aerodynamic principles. His mind didn't recognize the boundaries between disciplines that formal education tends to establish, which is precisely what allowed him to look at an aerospace material and see a racing solution while everyone else was looking at racing materials to find racing solutions. The best damn garage in town deserves its own moment of appreciation because it was genuinely unlike any other racing facility of its era. While competitor teams were working in functional but utilitarian spaces, Yunick's operation had the feel of a research institution. Machine tools that most teams couldn't afford or wouldn't have known how to operate. Material testing equipment. Reference libraries. Connections to academic and industrial research communities that were completely atypical for a racing garage in Daytona Beach, Florida in the 1960s. Yunick cultivated relationships with engineers at General Motors, at aerospace contractors, at universities, at material suppliers. He traded information, offered consulting on problems that interested him, and used the resulting network to stay aware of developments in fields that most racing people weren't even monitoring. That's how he knew about Lexan when nobody else in NASCAR was thinking about it. He was paying attention to a wider world than his competitors were bothering to watch. Look, the list of Yunick's innovations beyond the Lexan windows is staggering in both length and creativity. The 7/8 scale Chevrolet story has become almost mythological in racing circles, and it deserves the detailed treatment it rarely gets. The NASCAR rules of the era specified that stock cars had to be based on production vehicle dimensions, but the tolerance in the inspection process was measured with tools and methods that had practical limitations. Yunick built a car that was geometrically similar to the approved Chevrolet in every proportion, but scaled down to 7/8 of the original dimensions in every direction. The car looked right. It passed visual inspection. It was only when someone applied precise measurement tools with genuine rigor that the discrepancy became apparent. The aerodynamic advantage of a smaller frontal area at superspeedway speeds was substantial. A smaller car punching a smaller hole in the air could run at the same engine output level and simply go faster because there was less aerodynamic resistance to overcome. That's not a subtle gain. That's a fundamental competitive advantage built into the basic geometry of the vehicle. The fuel capacity manipulation stories are equally legendary. Racing fuel regulations specified maximum tank capacity, measured at technical inspection before the race. Yunick developed multiple techniques for passing inspection with a compliant tank and then racing with additional fuel capacity that hadn't been measured. The basketball inflation method worked by placing a deflated basketball inside the fuel cell before inspection, having the inspector measure and approve the capacity, and then inflating the basketball after inspection to displace volume inside the tank, meaning that when fuel was added, the apparent fill volume was the approved amount, but the actual fuel carried was greater. The extended fuel line routing technique worked differently, using extremely long fuel delivery lines routed through unnecessary lengths of plumbing to carry additional fuel in the lines themselves beyond what the tank measurement captured. These weren't simple cheats. They were engineering solutions to regulatory problems, requiring genuine creativity, precise execution, and a deep understanding of both the regulations and their practical enforcement limitations. This is where it gets really interesting from a philosophical standpoint, because Yunick's relationship with the rules was more nuanced than the simple cheater narrative that some people apply to him. He wasn't randomly breaking rules for competitive advantage without regard for consequences. He was systematically identifying the gaps between what the rules intended and what the rules actually said, and then exploiting those gaps with engineering precision. That distinction matters enormously. The rules existed to create competitive equity and maintain the stock car identity of NASCAR racing. Yunick's modifications often preserved both of those goals while finding advantages that the rule writers hadn't anticipated because they were thinking about the problem differently than he was. The Lexan windows were a perfect example. NASCAR wanted transparent windows on the cars. They got transparent windows. The windows were arguably safer than what they replaced. The only thing Yunick had changed was the material. And the material the rule writers had assumed would be used had never actually been specified. The drivers who worked with Yunick were a who's who of NASCAR's golden age. Herb Thomas, who won 2 NASCAR championships out of Yunick's operation. Fireball Roberts, one of the most naturally talented drivers the sport has ever produced. Curtis Turner. Little Joe Weatherly. These weren't drivers who chose Yunick despite his reputation for creative rule interpretation. They chose him partly because of it, because they understood that the mechanical and engineering advantages his operation provided translated directly into competitive advantages on the track, which translated directly into their safety, their results, and their careers. A driver sitting in a Yunick-prepared car knew that every possible legal, semi-legal, and plausibly deniable advantage had been extracted from the regulations and built into the car beneath him. That knowledge was itself a confidence booster that drivers of that era, who faced genuinely life-threatening risks every time they strapped in, deeply valued. The relationship between Yunick and NASCAR officials deserves its own examination because it was genuinely complicated in ways that simple narratives of rebel versus establishment fail to capture. Bill France Sr., who founded NASCAR and ran it with an iron hand for decades, both needed Yunick and was frequently infuriated by him. Yunick's cars drew attention, they won races, they generated stories. They made NASCAR more interesting, more technically compelling, more worthy of coverage in publications that wouldn't otherwise have paid attention to stock car racing. At the same time, every time Yunick found a new loophole, the sanctioning body had to respond, either by closing the gap explicitly in the rulebook or by accepting that the innovation would spread to the entire field and the competitive equity concern would resolve itself through universal adoption. France understood, even when he was threatening Yunick with lifetime bans, that the sport needed people like him to evolve technically. A racing series that stagnated technically would eventually stagnate competitively and commercially. Yunick's relentless pressure on the boundaries of the possible kept the technical development of NASCAR moving forward faster than it would have otherwise. The broader lesson that Yunick's career teaches about innovation is one that extends far beyond motorsport, and it's worth spending some time with because it applies directly to how breakthroughs happen in virtually every field of human endeavor. The standard narrative about innovation tends to focus on invention, on the creation of something genuinely new that didn't exist before, but Yunick's greatest contributions, and the Lexan windows are the perfect example, weren't inventions in that sense at all. Lexan already existed. It had existed for 15 years before Yunick brought it to NASCAR. The material science was established. The manufacturing process was proven. The aerospace and military applications had already demonstrated the material's performance characteristics across a wide range of demanding conditions. What Yunick contributed wasn't the material. It was the recognition that the material belonged in a context where nobody had thought to put it yet. That's a fundamentally different kind of innovation, and in many ways it's harder than pure invention because it requires you to simultaneously understand 2 different worlds well enough to see the connection between them that experts in either world individually would miss. This cross-domain pattern of innovation is actually far more common in the history of technology than the lone inventor creating something from nothing narrative that tends to dominate popular accounts. Velcro came from a Swiss engineer looking at the way burr seeds attached to his dog's fur and asking whether that mechanism could be engineered into a fastening system. The structure of DNA was partially worked out by applying X-ray crystallography techniques developed in physics to a biological problem. The touchscreen technology in your smartphone traces back to research done for military radar systems. In each case, the breakthrough came not from inventing something new within a single domain, but from recognizing that something proven in one domain had unexplored potential in another. Yunick was doing exactly this when he looked at aerospace polycarbonate and saw NASCAR windows. He was operating as a cross-domain connector, someone with enough breadth of knowledge and enough freedom from conventional assumptions to see possibilities that specialists couldn't see precisely because their expertise had made certain assumptions invisible to them. Here's the thing about why specialists often miss these cross-domain opportunities. Expertise is built through immersion in a field, and that immersion inevitably creates a kind of cognitive framework that shapes what you notice and what you filter out. A NASCAR crew chief in 1968 thought about windows in terms of NASCAR windows. Glass was the category. Different types of glass, different thicknesses, different installation methods, those were the variables within the category. The category boundary itself, the assumption that windows were a glass problem, was invisible because it had never needed to be questioned within the domain of stock car racing. Yunick's advantage was that he operated across multiple domains simultaneously. He thought about aerospace materials. He thought about military applications. He thought about production engineering. He thought about racing. And because he moved between these worlds, the category boundaries that were invisible to specialists were visible to him as the arbitrary constructs they actually were. Windows didn't have to be glass. That was never a law of physics. It was just a habit of thought that had never been challenged in the right context. Now, you might be thinking that this all sounds very abstract and philosophical for a video about race car windows. But here's why it matters practically, not just historically. The same dynamic that allowed Yunick to see Lexan where everyone else saw glass is operating right now in every field of human activity, including motorsport. There are materials, technologies, and techniques proven in other domains that haven't yet been recognized as solutions to problems in racing. There are racing solutions that haven't yet been recognized as applicable to medical devices, or construction materials, or consumer electronics, or any of 100 other fields that seem superficially unrelated. The people who will make those connections are the ones who, like Yunick, are paying attention to a wider world than their immediate competitive context requires them to watch. The lesson isn't just historical appreciation for a clever mechanic. It's a practical template for how to think about innovation in whatever domain you're operating in. The Formula One adoption of polycarbonate glazing is worth examining in detail because it happened differently from the NASCAR adoption and reveals something interesting about how different racing cultures process innovation. Formula One in the late 1960s and early 1970s was simultaneously the most technically sophisticated and the most conservatively traditional of the major racing series. Teams like Lotus, Ferrari, and Brabham were doing genuinely advanced aerodynamic work, developing ground effects, experimenting with unconventional suspension geometries, pushing the boundaries of what was technically possible in ways that NASCAR wasn't remotely approaching. But Formula One also had deep traditional attachments to certain ways of doing things, and a tendency to be skeptical of innovations that came from outside its own technical community. The fact that polycarbonate windows had demonstrated their value in American stock car racing was, if anything, a slight mark against them in the eyes of some Formula One engineers who maintained a somewhat dismissive attitude toward NASCAR as a technically serious enterprise. What changed the Formula One perspective wasn't the NASCAR data. It was the independent recognition by Formula One engineers that the weight savings and safety benefits were real and substantial regardless of where the idea had originated. Colin Chapman at Lotus, who was perhaps the most weight-obsessed constructor in Formula One history and the man responsible for the famous directive to add lightness as the core design philosophy, saw the polycarbonate data and understood immediately what it meant. Chapman didn't need Yunick to explain it to him. He could read the material specifications and run the same weight calculations that Yunick had run and arrive at the same conclusion independently. The Lotus adoption then influenced other teams through the competitive dynamics of Formula One, where a weight advantage visible in lap time data gets copied faster than almost anything else because lap times are publicly available and the pressure to match competitive innovations is enormous and immediate. The weight obsession in Formula One deserves its own moment of context because it helps explain why polycarbonate glazing found such enthusiastic adoption there once the resistance was overcome. Formula One cars of the late 1960s and early 1970s weighed dramatically less than NASCAR stock cars. Where a NASCAR machine of the era tipped the scales at over 3,400 pounds, a contemporary Formula One car weighed somewhere between 1,100 and 3,000 pounds depending on configuration. At that total vehicle weight, removing 30 or 40 pounds of glass and replacing it with 15 or 20 pounds of polycarbonate represents a proportionally much larger improvement than the same swap on a heavier stock car. The percentage gain is bigger. The performance impact per pound saved is larger because the total vehicle inertia is smaller. Formula One's weight sensitivity made Yunick's concept even more valuable in that context than it had been in the context where it was originally developed, which is another lesson about cross-domain innovation. Sometimes an idea that is good in its original context becomes even better when applied somewhere else, because the conditions in the new context amplify the benefit. The safety dimension of polycarbonate glazing in Formula One also carried particular weight, no pun intended, during this specific period. The late 1960s and early 1970s were a time of genuine crisis in Formula One safety. The sport was losing drivers at a rate that would be considered absolutely unconscionable by modern standards. Jim Clark killed in 1968. Piers Courage, killed in 1970, died. Jochen Rindt, killed in 1970, posthumously becoming the only Formula One world champion to have won the title after his death. Roger Williamson, killed in 1973. Francois Sever, killed in 1973. Peter Revson, killed in 1973. Peter Revson, 1974. These were not freak occurrences. They were symptomatic of a sport operating at performance levels that had dramatically outpaced its safety engineering. In that context, a glazing material that eliminated flying glass as a hazard in crashes, that maintains structural integrity under impacts severe enough to destroy glass panels completely, was not just a performance improvement. It was a genuine step toward making the sport less likely to kill its participants. That combination of performance benefit and safety improvement gave polycarbonate glazing a moral weight in Formula One adoption discussions that pure performance innovations didn't carry. Jackie Stewart, who was the most prominent advocate for improved safety in Formula One during this period, and whose campaigning eventually led to fundamental improvements in circuit design, marshal training, medical facilities, and car construction standards, was particularly vocal about the benefits of eliminating glass for race cars. Stewart had experienced firsthand the consequences of glass failure in racing incidents, and he understood with the clarity that comes from personal exposure to danger that the materials surrounding a driver in a crash weren't just structural components. They were the difference between walking away and not walking away. His advocacy added a prominent public voice to what might otherwise have remained a purely technical conversation among engineers, and it helped accelerate adoption across the Formula One paddock in ways that engineering arguments alone might not have achieved as quickly. The drag racing adoption story runs an almost perfect parallel with the Formula One story, but arrives at the same destination through a completely different cultural pathway. Drag racing has always had a relationship with innovation that is simultaneously more open and more chaotic than either NASCAR or Formula One. The sport attracts a particular kind of mechanical obsessive, someone who is willing to try almost anything in pursuit of a few hundredths of a second improvement in elapsed time, and who doesn't have the institutional conservatism of a large team organization filtering their decisions. When word reached the drag racing community that teams in NASCAR were running plastic windows and saving substantial weight, the response was essentially immediate. Drag racers didn't need a sanctioning body to approve the innovation. They didn't need multiple seasons of competitive pressure to overcome traditional resistance. They just needed to know it worked and understand why. And then they started doing it themselves at a rate that made NASCAR's adoption look leisurely by comparison. The National Hot Rod Association's technical regulations at the time were, like NASCAR's, somewhat ambiguous about window materials in ways that permitted polycarbonate without explicitly approving it. The NHRA's approach to the innovation was different from NASCAR's partly because the safety argument was even more compelling in drag racing than in stock car racing. Top-fuel dragsters and funny cars were operating at performance levels that made NASCAR's superspeedway racing look almost sedate by comparison. Vehicles accelerating to over 300 miles per hour in under 4 seconds, with nitromethane fuel systems capable of catastrophic fire and crash scenarios, demanded the most protective possible materials in every component. Glass that could shatter into projectiles in a crash was a problem that polycarbonate solved definitively. And in drag racing, that safety argument was sufficient on its own to drive adoption even before the weight benefits were fully quantified. The cumulative effect of adoption across NASCAR, Formula One, IndyCar, drag racing, sports car racing, and rallying over the course of roughly a decade, from the late 1960s to the late 1970s, was to transform polycarbonate glazing from a creative loophole exploited by one unconventional mechanic into the universal standard for motorsport glazing worldwide. By the early 1980s, the question was no longer whether a serious race car would use polycarbonate windows. The question was which grade of polycarbonate, which surface treatments, which installation method, and which supplier. The innovation had completed the full journey from radical to revolutionary to standard to obvious, the trajectory that every successful innovation follows if it genuinely delivers the performance it promises. The production car influence deserves deeper examination than it typically receives in discussions of Yunick's legacy, because the pathway from racing innovation to road car application wasn't as straightforward as the motorsport to production narrative usually suggests. It wasn't simply a case of manufacturers seeing what worked in racing and copying it directly into the road cars. The process was more complicated, more interesting, and ultimately more revealing about how technical innovation actually propagates through industries. The first production vehicles to seriously incorporate polycarbonate glazing were, predictably, the ones with the strongest philosophical and commercial connections to motorsport. Ferrari's use of Lexan in the F40 is the most famous example, but it represents the endpoint of a development process that had been running for over a decade before that car appeared in 1987. Throughout the 1970s, Ferrari had been using polycarbonate components in their racing programs, gaining direct experience with the material's behavior across a wide range of operating conditions. The engineers who designed the F40's weight-saving measures weren't taking a leap of faith with an unfamiliar material. They were applying accumulated knowledge from years of racing application to a road car context where the same benefits, lighter weight, better impact resistance, the ability to form complex curves, were equally valuable. Porsche's approach was characteristically methodical and revealed a different pathway from racing to production application. The company's motorsport division operated with a close technical relationship with the production engineering teams that was more formally structured than at most other manufacturers. Innovations proven in racing programs were systematically evaluated for production applicability through a defined process that considered not just performance benefits but manufacturing feasibility, cost implications, durability over production vehicle service life cycles, and regulatory compliance across multiple markets. Polycarbonate glazing moved through this process over several years, with the motorsport team's experience providing the initial performance data and the production engineering team working out the adaptations necessary to make the material viable in a vehicle that would be driven by customers rather than professional racing drivers under controlled conditions. The differences in operating environment between a racing application and a production application were significant enough to require genuine engineering work rather than simple direct transfer, but the fundamental case for the material was proven by the racing data, and that made the production adoption decision much lower risk than it would otherwise have been. The regulatory dimension of production vehicle polycarbonate adoption created complications that the racing world, with its relatively contained regulatory environment, hadn't had to navigate. Road vehicles operate under safety regulations in every market where they're sold, and those regulations had been written with glass in mind. Windshield regulations in particular specified optical distortion limits, abrasion resistance requirements, and impact performance standards that were all calibrated against glass performance characteristics. Polycarbonate met or exceeded the actual safety intent of most of these requirements, but it didn't always comply with the specific test methods and measurement standards that had been designed around glass properties. Getting polycarbonate glazing approved for road use in multiple markets required working with regulatory bodies to either demonstrate compliance with existing standards through alternative test methods or to develop new standards that measured actual safety performance rather than material-specific properties. This regulatory engagement took years in some markets and is one of the reasons that polycarbonate glazing in production vehicles spread more slowly than the performance case alone would have suggested. The automotive supply chain implications were substantial and often overlooked in technology adoption discussions. The established glass suppliers who had served the automotive industry for decades had massive investments in glass manufacturing infrastructure, established relationships with every major manufacturer, and understandable commercial incentives to resist or slow the adoption of a competing material. Their lobbying of regulatory bodies to maintain glass-specific standards was not subtle, and it was at least partially effective in some markets. This isn't a conspiracy narrative. It's simply the normal behavior of established industries facing disruptive competition from alternative technologies. Behavior that has been documented in industry after industry, from steel versus aluminum in automotive structures to film versus digital in photography. The racing world had been largely immune to this dynamic because the performance argument was so clear and the regulatory environment was relatively simple. The production vehicle world was more complex, with more stakeholders, more regulatory touchpoints, and more entrenched commercial relationships, all of which slowed but ultimately couldn't prevent the adoption of superior technology. Here's what most people don't realize about the current state of polycarbonate glazing in production vehicles. The adoption that started with exotic supercars in the 1980s has been progressively moving down the market toward mainstream vehicles, driven by a factor that Yunick never explicitly considered when he was thinking about windows in 1968. But that has become one of the most powerful forces shaping automotive engineering in the 21st century. That factor is fuel economy regulation. The corporate average fuel economy standards that govern vehicle fleets in the United States and equivalent regulations in Europe, China, and other major markets create an overwhelming incentive for manufacturers to reduce vehicle weight across their entire product lineup, not just in exotic performance vehicles where buyers accept premium pricing for weight-saving measures. Every pound removed from a mainstream vehicle improves its fuel economy, which helps the manufacturer's fleet average compliance, which avoids regulatory penalties and enables the continued sale of heavier, more profitable models. In this regulatory context, polycarbonate glazing has moved from a performance luxury to a mass-market weight reduction strategy, with major suppliers now offering polycarbonate glazing systems for mainstream vehicle programs in volume numbers that would have seemed inconceivable to the aerospace engineers who originally developed the material. The surface hardening technology that was developed to address polycarbonate's scratching vulnerability in racing applications became the key enabler for this mainstream production adoption. Early polycarbonate glazing scratched too easily for production vehicle use, or customers expected their windows to maintain optical clarity through years of normal use, including contact with automated car wash equipment, ice scrapers, and the general mechanical abuse that production vehicles experience in daily operation. The plasma-deposited hard coating technologies that were developed and refined to racing applications created polycarbonate surfaces with abrasion resistance approaching glass while maintaining all the weight and impact advantages of the base material. These coatings, which deposit a microscopically thin layer of silicon dioxide or similar hard material onto the polycarbonate surface through a plasma process, were themselves an innovation driven by the demanding requirements of motorsport application and then transferred to production vehicle use. The technology tree that grew from Yunick's original Lexan windows had branched in directions that nobody in that Daytona Beach garage could have anticipated. The heads-up display integration that represents the current frontier of racing windshield technology is perhaps the most striking illustration of how far the technology has traveled from its origins. Modern racing windshields are no longer simply transparent barriers against wind and debris. They are active information display systems that project telemetry data, navigation information, and situational awareness cues directly into the driver's visual field, without requiring them to look away from the track. The polycarbonate substrate that makes this possible is fundamentally the same material Yunick first used, but it has been engineered with embedded optical elements, specific refractive index profiles, and precision surface geometries that allow projected images to appear to float in space ahead of the car at a focal distance that doesn't require the driver's eyes to refocus from their normal forward viewing distance. The weight advantage that originally motivated the switch to polycarbonate is now almost secondary to the informational and operational advantages that the material's optical engineering enables. Yunick wanted lighter windows. He got a platform for an entirely new category of driver information technology that wouldn't have been possible with glass. The NASCAR Next-Gen car that was introduced for the 2022 season represents a particularly interesting data point in this technological evolution because it treats the polycarbonate windshield in a fundamentally different structural role than any previous NASCAR design. In earlier generations of NASCAR stock cars, the windshield was essentially a transparent panel installed in an opening in a steel structure that derived its strength from the roll cage and body panels. The windshield contributed little to the car's structural integrity and could be removed and replaced relatively easily. The next-gen car's windshield is bonded to the chassis structure using adhesive systems that make it a structural element, contributing to the torsional rigidity of the front of the car and participating in load transfer during crash events. The material that Yunick brought into the sport as a regulatory workaround, a clever substitution of one transparent material for another, has become so trusted and so well understood that designers now build their structural concepts around it rather than simply installing it into a structure designed around something else. That's the ultimate measure of a technology's maturation. When engineers stop treating it as a substitute for the original and start designing specifically to exploit its unique properties. The environmental sustainability angle that has become increasingly important in automotive and motorsport discussions adds another dimension to the Lexan legacy that would have been essentially invisible to Yunick in 1968, but that matters considerably in the current context. Conventional automotive glass, particularly the laminated safety glass used in windshields, presents significant end-of-life recycling challenges. The lamination layer that bonds the glass plies together makes separation difficult, and most laminated glass ends up in landfill rather than being recycled into new glass products. Polycarbonate, by contrast, is a thermoplastic that can be melted and reprocessed into new polycarbonate products relatively straightforwardly, assuming it isn't too heavily contaminated with coatings or embedded materials. Racing polycarbonate, which is replaced frequently and in relatively clean condition, is particularly amenable to recycling, and several major racing series have developed programs to collect and recycle used polycarbonate glazing rather than disposing of it. The reduced weight of polycarbonate compared to glass also means less material consumed per vehicle, less energy required to transport the vehicle throughout its service life, and less mass to dispose of at end of life. From a life cycle environmental perspective, polycarbonate glazing compares favorably to glass across multiple metrics, adding a sustainability argument to the performance and safety arguments that originally drove adoption. The human stories embedded in the Lexan revolution extend beyond Yunick himself to the drivers, engineers, and technicians whose careers were shaped by working with the technology as it developed. Mechanics who learned to work with polycarbonate in racing environments in the late 1960s and early 1970s carried that expertise into careers in aerospace, automotive production, and industrial manufacturing. The hands-on knowledge of how to cut, form, bond, and maintain polycarbonate glazing that they developed in racing contexts was genuinely specialized and genuinely valuable in a world where the material was expanding into new applications faster than formal training programs could develop practitioners. Racing served as an inadvertent trade school for a generation of polycarbonate technicians whose skills were in demand across multiple industries. That human capital flow is another dimension of motorsport's broader economic and technological contribution that rarely appears in discussions focused on the more visible technology transfer stories. The final chapter of the Lexan story isn't really a chapter at all, because the story hasn't ended. It's still being written in every racing garage on Earth, in every material science laboratory working on next-generation polycarbonate formulations, in every production vehicle engineering program looking for the next pound of weight reduction that improves fleet fuel economy compliance, and in every regulatory body working to update standards written for glass to accommodate a world where polycarbonate has become the default rather than the exception. Understanding where the technology is going requires understanding the forces driving its continued development, and those forces are, if anything, more powerful now than they were when Yunick first brought Lexan sheets into his Daytona beach garage. The weight reduction imperative that motivated Yunick has only intensified as vehicle performance expectations have risen and fuel economy regulations have tightened simultaneously. The safety improvement mandate that Jackie Stewart and others championed in the 1970s has evolved into a comprehensive safety engineering culture in which every material choice is evaluated against crash performance data with a rigor that didn't exist in Yunick's era. The informational technology integration that is transforming racing windshields into active display surfaces is accelerating as processing power, display technology, and optical engineering capabilities all advance simultaneously. And the sustainability requirements that are reshaping manufacturing across every industry are creating new pressures and new opportunities for polycarbonate glazing as alternatives to materials with worse environmental profiles. The next generation of polycarbonate glazing is being developed around the set of performance requirements that would have seemed like science fiction to the engineers who first adapted aerospace Lexan for NASCAR use. Electrochromic polycarbonate panels that can shift from fully transparent to deeply tinted in response to electrical signals are moving from laboratory demonstration toward practical racing application, offering drivers the ability to manage glare and light transmission in real time without fixed tinted panels that compromise visibility in certain lighting conditions. Embedded heating elements fine enough to be optically invisible are being integrated into polycarbonate windshields to provide defrosting and defogging capability without the weight penalty of separate heating systems, addressing one of the practical limitations that has constrained polycarbonate adoption in certain racing categories and production vehicle segments. Self-healing surface coatings that can repair minor scratches through thermal activation are being developed specifically to address the scratching vulnerability that has been polycarbonate's most persistent practical limitation since Yunick's crew first struggled with it in 1968. The material is still recognizably the same polycarbonate that General Electric scientists developed in 1953, but the engineering built around it has become extraordinarily sophisticated. The augmented reality windshield development that several major racing series and multiple production vehicle manufacturers are actively pursuing represents perhaps the most transformative near-term application of the polycarbonate platform. Unlike the heads-up display systems currently in use, which project a limited set of information onto a small area of the windshield surface. Full augmented reality windshields would overlay digital information across the entire forward view, highlighting track limits, displaying competitor positions, showing braking points, and providing situational awareness data in ways that are spatially registered to the actual physical environment the driver is looking at. The technical requirements for this capability are extraordinary. The polycarbonate substrate must maintain optical precision across its entire surface area, rather than just in the driver's primary forward sightline. The embedded optical elements that enable the display must be uniform enough that they don't create visible artifacts in normal forward viewing. The processing systems that generate the display must operate fast enough that the augmented reality overlay stays synchronized with the driver's head movement without perceptible lag. Meeting all of these requirements simultaneously while maintaining the weight, safety, and durability performance that racing applications demand is a genuine engineering challenge, but the pieces are coming together faster than most outside observers realize. Here's what most people don't realize about how close this technology actually is to widespread racing deployment. Several Formula One teams have been working with augmented reality windshield prototypes in simulator environments for several years, developing the software systems and display algorithms in advance of the hardware being ready for track use. The FIA, Formula One's governing body, has been engaged in conversations about the regulatory framework that would govern augmented reality display systems since at least 2019, which suggests that the governing body considers deployment within a foreseeable timeframe realistic enough to warrant regulatory preparation. IndyCar's series organizers have been in discussion with technology suppliers about augmented reality systems that could provide real-time competitor position information to help drivers navigate the complexities of oval racing where drafting partners and traffic management are critical strategic elements. NASCAR has been exploring augmented reality applications that could provide officials with enhanced tools for monitoring racing incidents and enforcing regulations in real time. The windshield that Yunick repurposed from aerospace application to save 75 pounds is on the verge of becoming the primary interface between drivers and a comprehensive real-time information ecosystem that manages everything from competitor positioning to energy deployment strategy. The production vehicle augmented reality windshield development is running on a parallel track with the racing applications and is being driven by the autonomous and semi-autonomous vehicle development programs at virtually every major manufacturer. Vehicles that share driving responsibility between human drivers and automated systems need new ways to communicate the system's current state, intentions, and limitations to the human occupant, and augmented reality windshield displays offer a spatially intuitive way to do this that conventional instrument clusters and heads-up displays can't match. When the automated system identifies a pedestrian at risk of stepping into the road, highlighting that pedestrian in the driver's forward view with a colored overlay is more immediately communicable than any instrument cluster warning. When the navigation system determines that a lane change is advisable, showing the recommended path as an overlay on the actual road ahead is more intuitive than any arrow on a screen. The polycarbonate windshield is becoming the primary human-machine interface in vehicles of all types, and the engineering investment being made in production vehicle augmented reality systems is in turn accelerating the development of capabilities that will flow back into racing applications, continuing the bidirectional technology transfer that has characterized the relationship between motorsport and production vehicles throughout the Lexus story. Look, stepping back from the specific technology trajectory and returning to the broader lesson that Yunick's innovation offers, there's something important to be said about the role of individuals in technological change that tends to get lost in institutional narratives about research programs and development roadmaps. The polycarbonate glazing revolution in motorsport didn't happen because a sanctioning body commissioned a study on alternative window materials. It didn't happen because a manufacturer's research department identified it as a strategic priority. It didn't happen because a material supplier mounted a successful marketing campaign to persuade racing teams to try their product. It happened because one person, operating with curiosity and creativity and a refusal to accept that the way things had always been done was the only way they could be done, looked at a material that existed in one context and saw its potential in another. The institutional adoption, the regulatory accommodation, the industrial development, all of that followed from that initial individual insight. Without Yunick's particular combination of broad technical knowledge, cross-domain awareness, and willingness to act on unconventional ideas despite the resistance he knew he would face, the polycarbonate glazing revolution in motorsport might have been delayed by years or even decades. Individual agency matters in technological change in ways that retrospective institutional narratives tend to obscure. The question of what Yunick would be doing if he were operating in today's racing environment is genuinely interesting to consider, not as idle speculation, but as a practical exercise in applying his analytical framework to current conditions. The low-hanging fruit that characterized his era, fundamental material substitutions and basic weight reduction opportunities that nobody had thought to pursue, are mostly harvested now. Modern racing teams employ engineers whose entire job is to find the kind of opportunities Yunick pursued instinctively, and they use computational tools of extraordinary power to search through the design space systematically. The obvious stuff gets found quickly now. But here's the thing about Yunick's approach that made it distinctive. He wasn't looking in the obvious places. He was looking in places that other people's assumptions had made invisible. And those invisible places still exist in modern racing, just as they exist in every mature technical field. The assumptions that current practitioners make without examining them, the category boundaries that nobody questions because they've always been there, the cross-domain connections that specialists in any single field can't see because their expertise has made the boundaries between domains feel natural and inevitable. Yunick would be looking there, wherever there happens to be in the current landscape of racing technology. The additive manufacturing revolution that is currently transforming component production in Formula One and beginning to influence other racing categories is one area where Yunick's framework would likely identify opportunities that the institutional development process is missing. Three-dimensional printing of metal and polymer components has been adopted enthusiastically for parts where the geometric freedom it enables performance improvements, impossible with conventional manufacturing. But the assumptions about which materials are appropriate for additive manufacturing, which applications benefit from the technology, and how additively manufactured components should be designed and validated are all still relatively young and relatively unexamined. A Yunick-style thinker looking at additive manufacturing and racing would be asking not just how to use it better within current paradigms, but which fundamental assumptions about component design, material selection, and system architecture become invalid when additive manufacturing removes the constraints imposed by conventional manufacturing methods. The answers to those questions are not yet obvious, which means they are exactly the kind of opportunity that Yunick's approach was designed to find. The energy storage and deployment systems that are becoming increasingly central to racing technology as hybrid and electric powertrains expand their presence in motorsport offer another domain rich with Yunick-style opportunity. The fundamental assumptions about how energy storage systems should be configured, where they should be positioned in the vehicle, how they should interact with mechanical systems, and what trade-offs are acceptable between energy density, power density, weight, and durability are all still being actively negotiated in racing contexts. The teams and engineers who will find the non-obvious advantages in this space will be the ones who can look at energy storage technology from outside the established frameworks, who can see connections to applications in other fields that racing specialists haven't considered, and who have the courage to pursue unconventional configurations despite the institutional resistance that unconventional ideas always generate. That's Yunick's template applied to a new domain. And it's as valid now as it was in 1968. The enduring relevance of Smokey Yunick's approach to innovation isn't really about race cars or windows or polycarbonate at all. When you strip it down to its essential elements, it's about the value of questioning assumptions that everyone else treats as invisible. It's about the power of cross-domain knowledge and identifying opportunities that domain specialists can't see. It's about the courage to pursue unconventional ideas in environments that reward conformity and punish deviation from established practice. And it's about the compounding nature of genuine innovation, how a single insight pursued with rigor and conviction can generate consequences that extend far beyond the original context, in directions that nobody, including the innovator, could have predicted. Yunick wanted lighter windows. He got lighter windows. He also got safer windows, a new industry, a generation of material science advances, production vehicle technology that has reached millions of cars worldwide, and a platform for the augmented reality display systems that are about to transform how drivers interact with their vehicles in both racing and road contexts. The butterfly effect of genuine innovation is always larger than it appears at the moment of origin. The next time you watch a race, any race, on any track, in any category, take a moment to look at those windows. They look unremarkable. They look obvious. They look like they couldn't possibly be anything other than what they are, That's exactly how you know the innovation has fully succeeded. The most profound changes always end up looking inevitable in retrospect, as if they couldn't have been otherwise, as if nobody could ever have thought it would be different. But it was different for the entire history of motorsport before 1968, and it took one mechanic with a wider frame of reference than his competitors, a willingness to be laughed at, and an absolutely unshakable conviction that glass windows on a race car were a problem waiting to be solved, to make the change that everyone now takes for granted. Drop your thoughts in the comments below about what you think the modern equivalent is. What accepted component or method in current racing everyone uses simply because that's how it has always been done. Because somewhere in that question lives the next innovation that will look completely obvious when someone finally makes it happen. And if racing history teaches us anything at all, it's that the person who makes it happen will probably be someone who, like Smokey Yunick, refuses to accept that the way things are is the only way they could ever be.